Well, thank you everybody for coming out here on a cold October night. I'm glad to see so many people from our community here. I just wanted to say a thank you also to the interactions.org, which has inaugurated Dark Matter Day throughout the world. There's now, last time I checked, 150 sites around the world that are holding events today at the same time. So we're going to try to have some brief remarks, brief for a physicist, remarks, where I hope we can give you a nodding acquaintance with the evidence that dark matter exists, and then discuss what our ideas about what the dark matter might be like, and how people around the world are trying to find it. This is, of course, going to be a quick overview, mainly meant to stimulate your questions for people who've been thinking about the dark matter who maybe don't work in that area. I will also introduce the panelists, well, first of all, when they arrive, if they're not here. But at the end of our prepared remarks, I will introduce them. And we'll start with Dr. Monika Lynker, who's going to tell us why we are so convinced that dark matter exists.
So this is my nod to Halloween. Thank you all for being here on Halloween. I'm going to very briefly introduce you to why we know that there is dark matter out there. And the dark matter that I'm talking about here is much darker than that cat that you see there. What we mean by dark matter as a physicist is really matter that does not emit any light at all. And it was Fritz Zwicky who coined the term. Fritz Zwicky was a Swiss astrophysicist. He named the matter dunkle Materie, that's the German term for dark matter, and he did this based on observations of the speed of galaxies in a cluster of galaxies. The cluster of galaxies is called the Coma cluster of galaxies. And what he did is he observed how fast these galaxies were moving with respect to each other, and based on that observation of how fast they're moving, he calculated back how much matter there must be in order for them to stay bound together as a cluster. And I'll explain this in a little bit more detail in a moment here. But he came up with a much, much larger number of the mass of what the cluster had to contain than what he could see as visible light in the cluster. And so the term dunkle Materie, dark matter, comes from the fact that he said there must be more out there than I can see, basically. Here is a picture of the Coma cluster. So like I said, the Coma cluster is a cluster of galaxies. There's about 1,000 galaxies in this picture. So all of these light smudges that you see in that picture are actually galaxies, not stars. The Coma cluster, if you look at it, extends about the width of your thumb in the sky, the width and the length of your thumb. So there is, if you look in the sky and you look at that area of the sky, there's 1,000 galaxies there somewhere, somewhere back there. A galaxy is a huge cluster of stars itself, right? So in each galaxy there is a couple of billion to a trillion to, depending on how big the galaxy is, trillions of stars in each of these galaxies. So what Zwicky did was measure the speeds of these galaxies, and this is, you can kind of think of this like in the solar system. So you know what the solar system, in the solar system we have all these planets that are circling the sun. They are doing that because of the force of gravity from the sun. So the sun, the force of gravity from the sun binds the planets in the solar system together. if you had something that was moving really fast coming into the solar system, that a comet or something like that, that comet would get deflected by the gravity of the sun. But the gravity of the sun might, depending on the distance where it is, might not be large enough so that it captures the comet. So it might just fly by and fly out of there again. And that's an object that is not bound then to the solar system and would not stick around. So in the same manner, these galaxies are all moving with respect to each other. And because they were moving faster than expected based on the amount of mass that there was, and with that on the amount of gravity, Zwicky was able to conclude that there must be a large amount of mass there that he couldn't see, that was dark enough that it did not emit any light at all. It's just the gravity that told him that it must be there. So this was in the 1930s that originated the term. A similar kind of logic was applied in the 70s by an astronomer called Vera Rubin and her collaborators. And what Vera Rubin did was she looked at the galaxies themselves. So what you see here on the picture is the Andromeda galaxy. That's the galaxy that is closest to us. It's very similar to our own Milky Way. And it consists of 1 trillion or so stars. And all of these stars are moving around the center of the galaxy. So here's the center of the galaxy, and we see this from our point of view a little bit edge on, but they are all moving sort of around the center this way. Our own solar system does that, and our Milky Way as well. So if this was the Milky Way, we would be somewhere out here on the outskirts of the galaxy, and our whole solar system moves around the center of the galaxy. It takes about, now I don't know, 200 million or so, a little bit more than 200 million years to get once around. So again, based on this relationship between the mass and with that the force of gravity that the center of the galaxy exerts, and the measured speed of the stars around the center of the galaxy, you can kind of conclude back what the speed ought to be, based on how much mass there is, how much visible mass there is, and then compare. And that's exactly what Vera Rubin did. So here is a picture of her, first of all, when she was at Vassar College as an undergraduate student looking through the telescope. What you see here is another picture of the Andromeda galaxy. This is out of their, her collaborator was Ken Ford, their 1970 paper. And these dark spots in here are the star system, or the stars where she took the measurements from. So each point on here is on the y-axis here you have the velocity with which these stars are moving, and on the x-axis you have the distance away from the center of the galaxy. And what you see is that when they're really close, the speed is not so large, then it rises, and then as you go further out, the stars that are further out, it looks almost like the speed is getting larger further out you go. Back there is a later paper that was the 1978 paper, where they had done the same kind of measurement for more galaxies, and we have since measured these same kinds of things for more and more galaxies. And we find consistently that the curves at the end here, where the stars are further out from the center of the galaxy, they are all what we call flat. So the speed as you go out does not decrease or increase, it stays the same. They are moving at the same speed. And that's not what we expect based on what we see from the visible light of the galaxies. What it looks like in the galaxy is that most of the mass is in the center of the galaxy, right here. And so it is sort of like the solar system, where most of the mass is in the sun, And when you think about the solar system, the Earth, which is closer to the sun, orbits the sun faster than Pluto, let's say, does, which is way out there. Pluto takes a lot longer to get around the sun than the Earth does. So what we would expect based on the visible mass distribution is that the speeds would decrease back here. So you would expect a curve that looks much more like this. And we don't see that in any of the galaxies. So the evidence here is that there must be more mass out there than we can see, again, just like with the Coma cluster that gave it a name originally. So I thought I'd take a few minutes to explain to you how we measure these speeds, right? I refer to speeds of galaxies, I refer to speeds of the stars around the center of the galaxy. How do we even know how fast these stars are moving? And the way we know this is from the Doppler effect. So the Doppler effect, you might have heard about the Doppler effect maybe in terms of the sound. That's better known than the Doppler effect for light. But what you might have noticed is that if you have a source of sound, for example, a train that's blowing their horn, if you stand in front of the train, it sounds a little bit different than if you stand, hopefully you don't stand right in front of the train, right? So stand to the side of the tracks. It will sound different when it comes towards you than when it goes away. You hear this even more clearly when you think about a Formula One racetrack or something like that. When you stand in front and the cars are coming towards you, it has a higher pitch, and then when they go past you, it's a lower pitch, right? Yeah. So the reason why that happens is because in front of the source of the sound, the waves are scrunched together like this. And in terms of sound, that corresponds to a higher pitch, a higher frequency. And in the back of the source of the sound, they are stretched out, and that is a longer wavelength and a lower pitch in terms of sound. So light waves do the same thing. Light is also a wave, and when you have a source of light, like a star or a galaxy, and that star or galaxy is coming towards you, then in front of that source, all those waves will be squished together, so to speak, and in the back, when it's moving away from you, they will be stretched out. So the next question, I suppose, is how do you see this for light? How do you determine how stretched out or how scrunched together the light waves are? And the way we do that is by looking at light from a source, from a star, for example, and splitting the light up into its component parts. And that's where those slides that you have on the tables come in. So what you have on the table is a cheap kind of diffraction grating. And when you hold that up and look at the light, what you should all see is sort of a rainbow of colors, right? So that white light that is coming from the overhead lamps is actually blue light and yellow light and green light and red light and everything mixed together, and your eyes make white out of this. And you see this continuous spectrum from those kinds of lamps, but if you would look at a pure element, so if you would look at a gas that discharges light and the gas consists just of hydrogen or just of mercury or whatever element you have, what you see instead is a set of very distinct lines. So here's an example of the rainbow colors, and then there are these dark lines in between. And these dark lines correspond very succinctly to the particular element. So astronomers can actually tell what kinds of elements are out in the stars by looking at the pattern in the lines that the light from the star is emitting. And when Vera Rubin and her collaborators did their research, this is actually sort of a part of a figure in their paper. It looks like this. So this is kind of a little bit of a cartoon of this. A modern spectrum will look more like this. This is an example of a spectrum that one of my colleagues, Dr. Hinnefeld, took with the observatory that's up on Northside Hall. So here this looks different. The dark lines in there are dips in the intensity of the light curve. So going back to the Doppler effect, if this is your reference spectrum, if you know that these are the lines that are coming from, let's say, hydrogen, when the hydrogen is at rest in a lamp, like in the back of the room, you can look at that afterwards, then you know which wavelengths you would expect. And if in the spectrum instead these lines are shifted towards the blue corresponds to shorter wavelengths, then you know that that star, the source, must be moving towards you. And if it's shifted more towards the red, like this one here, they're shifted towards this side, and here they're shifted towards the blue side. When it's shifted towards the red, it's the longer wavelengths, and the source is moving away from you. And the more they are shifted, the faster they are moving away or towards you. So that shift in the wavelengths tells you how fast the star is moving or how fast the galaxy is moving, depending on what you look at. So that is both of the evidence that I told you before is based on this kind of an idea. There's a third evidence that I would like to mention here, and that is the bullet cluster. So this is another cluster of galaxies. And what you see in this picture is two clusters of galaxies. So visibly, there's a cluster here and there's a cluster here. It's a smaller cluster than the coma cluster. And the light in here is the pink is light that is emitted from gas, and the blue is colored in there is dark matter. And what we think has happened here is that the two clusters of galaxies collided. So you have this thing here that looks like a cone. That's why it's called a bullet cluster. The bullet went through this way, and the gas makes that shape, and the dark matter is here on the outside because dark matter doesn't interact with each other. It went right through, and so it ended up on the outside here. That's the original, where the original cluster was, and that's where the original where the dark matter of the cluster that went through there ended up. And I have a simulation here where you can see how we think that this would have happened. So what you see here are these two clusters, these two blue blobs that are colliding with each other. They're going through each other. The dark matter doesn't interact with each other, so ends up on the front of the whole thing. The other dark matter stays behind, and it simulates pretty much exactly what you saw in the picture, in the previous picture, which was based on measurements. So, summary of what I talked about, the term dark matter comes from the observation of the coma cluster where there was missing mass that we couldn't see. The galaxy rotation curves gave the more exact evidence for dark matter. The bullet cluster is another indication that there is actually dark matter around. There's other evidence, and that includes the microwave background. So the microwave background is what we see from the very early universe, the radiation that's left over from the very early universe, and the way that large-scale structures, so clusters of galaxies are formed that could not have happened the way it did without dark matter either. And I'm not going to go into the details here. Instead, I leave the stage to you to tell us what it is or what it might be.
As Monika mentioned, I'm going to try to give you a sense of what our ideas are about the dark matter, what it might be like, and also the ways in which scientists around the world are trying to find it experimentally, individual bits of it. Dr. Lynker talked to you about how we know that the dark matter is there from the effects of dark matter gravitationally, so not from any individual bits of it. Right now, what we're trying to do around the world is find individual bits of it. So that's what I'll be concentrating on. So, well, actually, I'll skip this. This is something that Dr. Lynker already talked about. So, the first question is, what is the nature of this dark matter? Well, how do we generate ideas? We have to have ideas about what the dark matter might be like and then test them. Where do we take our ideas from? Some of the so-called natural ideas are ones that arise, are ideas that arise from other areas of physics where we are already working on problems, and they happen to provide dark matter candidates. And we call them natural only because we already know these other problems already exist, and they seem like they could be tied into the dark matter problem. There's another class of ideas called ad hoc ideas, where we invent ideas really focused on trying to answer the question, why is there dark matter? So one example of an ad hoc idea is the idea, well, maybe through some unknown physics in the very early universe, a very small fraction of a second after the Big Bang, a bunch of black holes were created. That's an ad hoc idea. An example of natural ideas are two of the big problems that we're trying to answer today in physics is, why is gravity so much weaker than the other forces in nature? The attempts to answer that lead to a field or a proposal called supersymmetry. I won't go into the details of that because I'm just trying to illustrate the method for generating guesses, and there's just too many to go through. But this general attempt to answer this big question provides as a side benefit candidates for the dark matter, weakly interacting massive particles that arise naturally from something that has nothing to do with all the astronomical evidence that Dr. Lynker talked to you about. Likewise, there's a big question that we don't know the answer to. Why do we live in a matter universe? In the very early universe, in the Big Bang, there should have been equal amounts of matter and antimatter created, and at some point, a small fraction of a second after the Big Bang, the amount of the matter and antimatter went through annihilation processes, and by some unknown process, we're left with only matter in our universe and almost no antimatter. And so attempts to understand the answer to that question, which go by, among other things, this name, also provide candidates, particles, sort of for free, which could be the dark matter. And so these are two examples of sort maybe more natural, let's be honest, guesses about what the dark matter is. Okay. I've given you just a couple of examples. I want to emphasize the point. Here's one of the first omissions that I referred to in the front of my slides. There are many ideas about what the dark matter might be like. This is a partial list of the names of different ideas about what the nature of dark matter might be. Some of them are ad hoc, some of them are natural. Okay? And this figure that you see here, the details aren't important, but these colored regions all refer to ideas that are over here. This is a plot which shows one property, effective size of the dark matter particle, and another property, the mass of the dark matter particle. And if we examine at some level these two axes, we're going to see something astonishing. The effective size, which is a measurement of how likely it is that dark matter would bounce into ordinary matter, spans a huge range of possible sizes. The biggest size is 1,000 trillion times bigger than the smallest effective size candidate. Likewise, there's a whole range of possibilities that each of these theories give to the mass of those particles. And the effective size ranges from the biggest one is 1,000 trillion times more massive than the least massive one. So the main point to make here is that, as you would expect from this, no one detector could test all these ideas. And so there's a large number of experiments, in the tens of experiments around the world, each of which is different, each of which, or many of which, are addressed at different regions in this theory plot. And today I'm just going to point out a couple. I'll point out one that's related to the type of dark matter search that we're doing at IU South Bend. And just for variety, I'll point out another example so you can see some of this variation in characteristics that I'm talking about. So these axions, which come from the question, why do we live in a matter universe and not an antimatter universe? One of the characteristics of a type of particle, the theory attempting to answer that question, produces is a particle called an axion, and this axion has very interesting properties. It can be created by the collision of photons, particles of light. And the sun generates enormous amounts of light from the fusion reactions going on there. When I'm talking about light, I'm speaking somewhat poetically because this is light that our eyes are not sensitive to. These would be gamma rays. And the light here is actually magnetic fields that are inside the sun. And so these particles of light can interact, annihilate, and create an axion particle, if this theory is true. And so the sun could be a source of these particles which were created in the early universe, but now would be intensely created inside the sun and streaming towards us. So we could set up detectors on the Earth to sort of reverse this process. You set up a big magnet, a very strong magnetic field, and these axions come through, and every once in a while the magnetic field from this very strong magnet will interact with the axion, turning into an X-ray. So we could see evidence for this, if it exists, by having a sudden amount of X-rays when we tune this detector just right. Now, each of these particles would be very, 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 very light in comparison with the types of dark matter that we're looking for. By the way, I do see a number of students in my class, so this will be familiar to you. If you have questions along the way, please, don't hesitate to stop me. I know we'll have questions at the end also, but if I've said something you don't understand, don't hesitate to raise your hand and call in. Okay. A different type of dark matter comes from those attempts to understand why is gravity so much weaker than the other forces. And as I mentioned, as a side benefit of that theory, one of the types of particles that would exist could exist if that theory is correct, is a so-called weakly interacting massive particle. So where would these things come from? These things would exist from a very early time in the universe, about a billionth of a second after the Big Bang. The universe was an extremely hot, dense state. And you had particles like photons colliding with each other, and electrons and positrons colliding with each other. And this is the one equation we're going to see the whole night, Einstein's relationship between energy and mass. And all this tells you here is that if you've got enough energy in collisions, you can make as big a mass as you want. That's what this relationship tells you. So in the very early universe, where everything was moving around very energetically, and when they collided, you could make really massive things. So the idea is that in the early universe, things were moving around so fast that these very large mass particles were created, and in the simplest version of the story, there are many versions of this story, the dark matter was being created and annihilated and reached sort of an equilibrium with ordinary matter. But then the universe started to cool when it expanded, kind of like a gas that if you blow air out of your mouth like this, it's very hot. If you let it expand when it comes out of your mouth like this, it's cooler. The universe was doing the same thing. So when the universe cooled off, the amount of energy went down, and suddenly you couldn't make dark matter particles anymore. But you were still annihilating dark matter particles to create ordinary particles. And so we started losing dark matter particles. But at some point, the universe expanded so much that dark matter particles couldn't find each other anymore because there's so much space for them to be in. And so the idea is that these dark matter particles have been frozen into the universe since that early time, about a billionth of a second after the Big Bang. And they're going through everywhere right now. Where are they? They're right here. They're going through your body right now. We know that they're in the Milky Way galaxy because, as Dr. Lynker described, we've observed the rotation of different parts of the Milky Way galaxy. And we know that there's about 85% of the mass that's unaccounted for. Only about 15% is accounted for by what I'm going to call atoms, which includes everything, including big clouds of gas and stars, black holes, etc. That's only about 15% of the stuff that's out there. And in fact, at our location, there's about one dark matter particle in every fist at any time. Okay, so one of the questions, since we want to find individual bits of the stuff, is how do we do it? And as you might have guessed already from what we talked about, there's a wide range of possibilities about what the nature of the dark matter could be, which makes designing something that can catch it very challenging. So this is an analogy that actually a podcaster suggested to me, which is, we don't know if the dark matter is more like a mole or a mouse or a bat. If it's like a bat, and we've designed things that can catch things that are underground, we'll never see them, etc. We can go through permutations of that. And that's why you'll see that we have many different techniques to try to see the dark matter. Let's take the macroscopic view. Even within this small subsection of dark matter candidates that we've narrowed our view down to, there's three general ways that we're looking for this type of WIMP dark matter. One, scientists are looking for dark matter that's annihilating, say, in the center of our galaxy. Annihilating and forming high energy particles that we can see, like photons, which would have characteristic energies that we could see. Another way that we're trying to see them is by making them in accelerators. And in fact, our colleagues at Notre Dame are participating in an experiment which is looking for dark matter in this way at the Large Hadron Collider in Europe. So they're smashing together protons at high enough energies. Remember our one equation, E equals mc squared, at high enough E that maybe they're making these large mass dark matter particles. And then three, there's people like the group at IU South Bend and our collaborators who are looking for dark matter by having targets of ordinary atoms that are sitting inside of a detector, and we're looking for these targets to suddenly scatter for no apparent reason. Okay. So again, I'm going to narrow our focus down to this type of technique. I won't talk any more about these two. When we're using this technique to try to look for dark matter, one of the big complications that we have to worry about, since dark matter interacts so weakly with ordinary matter, if we have anything else going through our detector that could look like a dark matter particle, that could be a problem. So one of the big things that we have to face is that there are cosmic rays constantly smashing into our atmosphere, mostly protons boiled off from the sun, but other particles coming from distant supernovae, etc., smashing into our atmosphere, creating a rain of cosmic rays that are going through you all the time. So we have to take our detectors deep underground. In fact, our experiment and several other dark matter experiments are in what I believe is the deepest mine in North America, in northern Ontario. And so we have to go deep underground so that all of these particles get absorbed, but the dark matter particles, well, to them, the Earth isn't even there, since they interact so deeply. The other thing that we have to worry about is background from radioactivity. Everything we see around us is somewhat radioactive because the Earth is formed from the debris of at least 2 ancient supernovae. So we have to make sure that we select all of the materials that we build these detectors out of so that they're low in radioactivity and develop techniques to clean them. And one of the things that I worked on in a previous experiment in the same location was methods for keeping radioactivity from our air. The air we breathe is radioactive from something that you may have heard about called radon. So we have to worry about all these types of backgrounds. That's why we have to do the experiments underground, and we have very special cleanliness requirements. So I'm going to talk about a couple of other experiments before I focus in on what we do at IU South Bend. This is an example of an experiment where essentially they're looking for the same thing we're looking for. A dark matter particle comes in, bumps an atom, and then the dark matter particle goes off on its merry way, and the atom, which is the only thing we can see here, suddenly moves for no apparent reason. This is a detector, the LZ experiment, which is based on liquid xenon. And they look for this bump, this very small energy bump of an atom by looking at the flash of light that's created from the initial bump. And that bump also liberates some electrons which get accelerated by an electric field up to a gas phase, and that creates a second flash of light. And what you see on the top and on the bottom are special light sensors. In fact, one of my former students is now a postdoc working on this experiment. This is another experiment that's looking for the dark matter. I guess I won't spend too much time on this, but this is another leading experiment in the field. They're looking for an atom to be bumped in a crystal that's very cold, and the way that they detect dark matter is to look for 2 signals. Again, electrons from ionization, and also very tiny vibrations in the crystal lattice that they can sense. And here you can see a photograph of modules of their detector. So now let's focus in again. Again, we're narrowing down to the experiment that IU South Bend is participating in with collaborators around the world. So we're basing our observation, again, a bump of an atom, on the superheated liquid technique. If you heat up a liquid like water, you can heat it actually above its boiling point, and unless there's a starter bubble, that water will stay above 100 degrees and sit there happily for a while if you put it in a very clean container and you don't disturb it. But if you do disturb it, it can explosively transform into a gas. And so you can amplify a very tiny signal into something that you can detect with cameras and with sound sensors. So here's an example of something you should never ever do at home. In fact, you should be careful about this. When you're heating water in your microwave oven, you can superheat water. That's water that's superheated in a glass in a microwave. And let's just play this 10-second clip. So the penny dropped in, which brought in a tiny air bubble, that's a starter bubble, and then the entire glass of water the water exploded into gas. You can get very bad burns from this, so you shouldn't try this experiment at home. Okay, so our experiment is based on that idea, though. We take a target of atoms a fluid that we heat above its boiling point, so that it's superheated and ready to explode into a gas, and we watch it with cameras, and we listen with acoustic transducers. This is the thing that IU South Bend contributes most to the experiment on. And when a dark matter particle or some other object like a neutron or radioactive decay comes in, it starts the formation of a bubble. You can see that right here. So this gives you an idea of the overall design of the experiment, and then we put pressure on with our compression system so that we don't have that huge explosion. Our software shuts that down very quickly, and here you can see acoustic traces. We're going to get back to that. Why is that important? Why do we have these sound sensors? Well, it turns out in 2008 that the IUSB team discovered that you can actually hear the difference between different subatomic particles in matter by the sounds they make. The bubbles they make different sounds. So here is an example from a paper published just a number of days ago. This is a plot which shows number of events and how loud the event was, how loud the bubble was. And what's shown in black is the sounds that were made by neutron sources, which create signals just like dark matter will create. And what you can see is that they made relatively quiet sounds, that calibration source. When we started to look for when we looked for dark matter, all of our data appears here and here, which we know from previous work is the signature of radon decay. So the reason that the sound sensors are so important, since we can see the bubbles, is that that tells us on an event-by-event basis, hey, this isn't dark matter, this is radioactivity, which is our main concern. We don't want to confuse radioactive decay with evidence for dark matter. And these sound sensors are what lets us do that. So I'm going to play for you the world's most boring movie ever while I explain a little bit about the detector. Oops. There we go. Okay, so this is a year's worth of data in one of our larger detectors, Q60 detector, Pico 60 detector. And the cylinders you see here are the acoustic transducers. This is the region where the superheated liquid is. There's water on top to keep it away from things that could cause bubbles for reasons other than dark matter. And all we saw in the paper that we recently published was events from radioactivity. But this boring movie, it turns out, produces the most stringent limits on the properties of dark matter that could exist for a certain type of candidate. With the caveat, remember that plot with the huge range of possibilities for candidates for dark matter. Okay. So what happens if, like this time, we didn't see dark matter? That's not a failure, that just allows us to restrict what the possible characteristics of dark matter are. So we produce plots that look like this, where we plot the effective size of the dark matter, how likely it is to hit an atom, with the range of masses that the dark matter particle can have. And our lack of observation allows us to say, well, any combination of properties anywhere in this region, not possible. The dark matter does not have those properties. So let's take just one quick look at the data. This is from our recent paper. Couple of things here. The colored in regions, these are the regions that the theorists, remember these are the theorists who are trying to understand why it is that gravity is so much weaker than the other forces, and their ideas lead to predictions like this for what the possible nature of dark matter could be like. And these different colored lines are the limits produced by other experiments, including 2 previous measurements that we did, and our most recent measurement, which you can see goes down to the smallest effective size in the world. But I would caution you, this is only for one type of favored candidate for dark matter. There are other experiments which are much more sensitive than us, looking for other candidates of dark matter. Right? And to date, there's been no confirmed observations of dark matter by any of the techniques. Okay, I wanted to move on a little bit to sort of the experience of trying to do this work. So this is a montage of photographs of a typical day that I had for about 5 years. This experiment is in northern Ontario, and it gets quite cold in the winter. The radio weather guy cheerfully announced it was going to warm up to minus 40 degrees. You get onto a cage in the morning. You go down a mile underground to protect us from cosmic rays. And it's an active nickel copper mine, so it's probably the filthiest place in the world. And yet, the Snow Lab Institute has created an extraordinarily clean place, which is necessary to suppress the radioactive background, which we talked about before. Here is a recent trip that some students from IU South Bend, including, I see Tom is back there, who's, by the way, going to be demonstrating some things in the back, some interactive demonstrations that you can look at to help understand some of the work that we're doing and also some of the broader impacts of the work that we're doing in the back. And Ed Benke, who's the engineer in our group, and 2 other students, Aaron, who's now a grad student at the University of Notre Dame, and Alex Leclerc, who is a computer scientist who's now working on other things. And this is the student who's working on a competing experiment. She's now a postdoc at Penn State working on the LZ experiment, which I told you about before. How are we doing for time? I will show you 2 minutes that just give you a feeling for what it's like to live the day of a scientist doing this type of work. We won't go too long on this. Not at all.
The Earth is constantly being bombarded with all sorts of junk coming in from space. We come underground because we have 2 kilometers of solid rock over our head. So that filters out all of that stuff that we don't want and leaves us only the stuff that we actually want to see.
So today we're in this little town in northern Ontario, and it's very early. It's still dark and it's snowing. It's not even 6 a.m. We're about to get in the car and we're going to go to this mine where we're going to actually travel deep underground and visit this lab that's one of the deepest labs in the world. And down there they're looking for these little particles, these tiny bits of matter that make up the entire universe.
Scientists at Snow Lab are probing the sun and distant stars for clues about how it all came to be. And our cameras were given a rare chance to check it out. But getting there takes a while. First, we dress like miners. Then we ride with miners on their way to work in the Cage, an elevator that descends to almost 7,000 feet.
So right now we're 2 kilometers underground in an active copper and nickel mine. We're hiking another 1 or 2 kilometers through the mine to get to Snow Lab, which is actually one of the cleanest lab spaces in the world.
We can't track in any dirt, so while our gear gets wiped down, we're sent to take a shower and change our clothes. Now for the science. These scientists are being lifted out of a massive cavern filled with ultra-pure water. It's shielding a detector looking for neutrinos, also known as the ghost particle.
Okay, so we're here at the Snow Plus experiment. This is what's down that hole. Like, what are these photos? This is beautiful.
So these are photos of the detector of our acrylic vessel, which is the center of the detector.
we be looking for neutrinos? Why do they matter?
They're a very good messenger of the reactions that create them. We've been studying them for decades and still have more questions about them.
Discoveries made here won the Nobel Prize in Physics in 2015 by revealing that neutrinos from the sun had mass. Now, Erica and her team are expanding their search.
What are you guys looking for?
We'll be looking at neutrinos from the Earth around us, geoneutrinos, neutrinos from reactors in Canada. So that can tell us more about what's going on in the sun than the light, which takes millions of years to get out.
Wow, so we can actually study the sun from deep inside a mine.
From 2 kilometers underground.
That's so cool.
Then there's dark matter. No one has ever found it, but it's the glue holding galaxies together, and this device could detect it.
This is Pico. This is what we're using. It's the same that's actually inside there.
What is dark matter?
Right. So dark matter is, well, basically something that we don't know what it is. We don't understand about a quarter of the universe, so about 27% of the matter that's out there, we have no idea what it is.
But it's down here in this mine?
It's down here in this mine. It's all the time. It's going through us all the time. It's going through the Earth. And it'll interact only really rarely, which is, of course, it's a great thing in that, it makes it down here. We can filter out everything else.
So do you think that someone, maybe hopefully you guys will find dark matter soon?
I'm really hoping so, yeah. We're getting to the point now where the limits are being driven down so far that if we don't find it soon, we're not going to find it for a while. We're going to have to think of a new way to detect it.
Okay, I think I'll stop that there. As I said, there's a human dimension to all of this. This is the IU South Bend Astroparticle Group as it currently is constituted. And there are interactive displays in the back, as I mentioned, by students to help you understand certain aspects of the work here. This is our group photo this past summer, and you can see some historical data on the 45 undergraduates who have contributed to this work, and also area high school teachers and high school students have contributed to this to this work as well. I also just want to just take this opportunity, since we're ending this discussion and getting ready for question period, just to thank all the people in the physics department at IU South Bend, especially Linda Kneffley, who helped organize tonight's event, and our guest panelists, who are theory specialists. Dr. Adam Martin is a theoretical physicist from the University of Notre Dame, and Dr. John Beacom is a physicist from the Ohio State University, and I'm contractually obligated to point out that he's a hunter for ghost particles. There are plenty of people to thank. I think there are very exciting times ahead, but I'm going to stop talking about this now. And are the people from QuarkNet here? No? Okay. All right. So I guess that isn't set up. So I guess maybe I will call our panelists up here and open up the floor to you. Questions that you have about what you've seen, anything that you want to know about. The floor is open to you now. Questions? Yes?
So, one of the theories was I believe, axion particles, correct? And you said that they were created from collisions of gamma particles, correct? And then when we detect them if we were to detect them with magnetic fields, we would we would detect X-ray radiation. Where's the extra energy?
You have to speak up, I can't hear.
Where's the extra energy lost between the collision of those gamma particles and the theoretical detected X-rays? Because the X-rays would be lower energy than the gamma rays.
Oh, well, they're converted into X-rays by interactions with the magnetic field inside of the inside of the detector. I'm not sure I heard
Well,
the question.
I think the question was, the energy of the gamma is higher than the energy of the X-ray. If you think about the conservation of energy principle, so if you have two gammas colliding with each other and you end up detecting X-rays, the question was, what happened to the other energy that didn't end up as a part of the X-ray? Wasn't that what?
Yeah,
Yeah.
more or less, yeah.
You guys have a good answer for amount of energy?
I would think that gamma rays are typically just the term anytime we use for that kind of particle, so it doesn't necessarily mean a specific energy. Classically, we think about gamma rays being a very specific energy, but we toss the term around kind of loosely to mean any particular energy. So I didn't see the exact collision that you're thinking about, but I imagine it was, you said the word gamma ray was really just a particle of slightly different energy, not necessarily what you might 20 years ago call gamma.
But the energy of the X-ray would be related to the mass of the particle, which is, I think, what you're asking.
I wasn't sure if there were other processes in collision, if there was any other radiation inside the sun, or if there was anything else going on.
Other questions? Yes.
Yeah, I'm not a astrophysicist or a physicist of any kind, so I ask you to bear with me with these questions. Perhaps
We're here for you.
yeah, I may sound uneducated regarding this, but is it possible there is no dark matter detected so far because there was no dark matter? Is it possible that the issue is not that there's matter out there? If I interpret what I'm being told here correctly, that the existence of dark matter is dependent on our current understanding of the laws of gravity. Is that accurate? Is that where it started? Gravity has to, gravity, there must be matter out there because matter is what creates gravity. And the way these galaxies are moving away from each other at faster speeds, by golly, if they're doing that, there must be matter out there that's controlling that. We just can't see it, can't smell it, can't hear it, can't taste it. But it's got to be there, or else there's something wrong with the laws of gravity. Why isn't there something wrong with the laws of gravity? I mean, if you look at the concept of quantum physics, the subatomic particles, we look at these. I'm sorry, was I interrupting? Yeah. If you look at what's going on in the quantum field, again, as I understand it, there's a lot of things that happen with particles subatomically that just don't seem to fit with our classic understanding of what goes on with regular matter up here. That experiment where the photons move, and no matter how far away you put them, the polarity and all that. So my question is, just as Einstein referred to that stuff as spooky motion, wasn't really sure about what the heck was going on down there, and I'm not certain right now we're still sure of what's going on that micro level. Is it not possible that the macro level, when you're talking about galaxies and galaxies and galaxies, is it not possible that at the macro level, gravity just acts differently? I haven't heard any talk about, is there experiments being done to establish or to look for different laws of gravity at that level?
I can help with that one. So that's a great question, and let's start with something basic. So we see the sun, and we see the planets orbiting the sun, and we know that they're orbiting the sun because of the gravitational force, right?
Yeah.
Okay. So now, what would happen if we saw a place where there's nothing, but we saw something going around and around it? And in that case, you would say, well, maybe there's something I don't see that's causing the gravity. And that would be a case where you can't just fix it by changing the law of gravity because you can't see the thing. Let me back up a step. So in the case of the sun, we see the sun and the planet goes around it. And in the case of the Milky Way, the stars orbiting the galactic center, we see stuff there, we see stars there. And the stuff that's moving around, it looks like its motion is telling us that there's more mass there than we think. That's the dark matter interpretation. The other interpretation, which you're right is a very good question, is maybe the laws of gravity are just different. And in the case of the stars orbiting the Milky Way galaxy, it's hard to tell because there is visible matter there, and maybe gravity is just behaving differently. So that's what I was trying to get to, is like, what if you had a case where there's nothing there, but something's going around and around and around? It must be attracted by mass. Now, in the case of a star orbiting like that, it could be orbiting a black hole, which is a tiny component of the dark matter. Yeah.
You have a case where there's something going around and around, and there's nothing there?
Right.
What's going around and around?
Well, say like a star is orbiting a spot where you don't see anything else.
Have you seen that?
So in that case, yes, and in that case, we know it's like a star orbiting a black hole. That's not really the dark matter, but it's an example of how that could work. There's another case that we've seen where we had basically a collision of two clusters of galaxies. It's called the bullet cluster. And in there, so here's before, there's some dark matter, and there's some gas, and there's some stars.
Okay, but we don't know there's dark matter.
That's right. Okay, but there's a collection of material. Here's what we see is the stars and the gas, and maybe there's dark matter, maybe not. This side, stars and gas, we see it, and maybe there's dark matter, maybe not. Now here's the cool thing. These passed right through each other, and what happened is the gas got stuck in the middle because the gas interacts with the other gas, and apparently the dark matter kept going, and we can see that it's there by the way that it bends light on the other side.
You see something bending.
Well, we see, okay, so there's a little tricky part. I said there's stars, there's gas, and there's maybe dark matter. The gas is easy to see. The galaxies, the stars are actually in galaxies, which are pretty little tiny lumps. And the little tiny lumps move right past each other. The gas gets caught up, and then the dark matter also, maybe if it's there, goes right through. And you can tell that the dark matter is there by the bending of light. And the bending of light cannot be accounted for by the amount of stars in those galaxies.
And I guess, that sounds very tautologic to me, like you're just going around and around, and you're coming right back to saying, well, there has to be gravity, that's the only thing that would make that move.
Well, no. We know, roughly speaking, how galaxies work, by which I mean, and how galaxy clusters work, by which I mean we know the fraction of atoms that are in stars and the fraction of atoms that are not in stars in a galaxy. Okay, we know that fraction. Likewise, we know the fraction of atoms in a cluster that are part of an individual galaxy, and the atoms that are just belong to the cluster as a whole. And by far, most atoms in these systems do not belong to any one galaxy. They just belong to the clusters. And that collision which we saw, remember the pink image, that was the atoms. Almost all the atoms stopped or slowed down. And yet, and remember, the most atoms in these systems are just the gas. That slowed down, but most of the mass went right through. So there's a separation of atoms and mass. And the ideas that you're referring to, things like MOND, which some people are still looking at. There are people who are trying to understand that and are pursuing the very point you're raising. That, MOND, Modified Newtonian Dynamics.
Or modified gravity.
Yeah.
So I want to emphasize that what you're asking is an absolutely valid question, and it's something that we're trying to figure out. There are two different theories, right? Gravity is modified on galactic scales, or there's more mass than we thought and gravity is the same. And based on the preponderance of the evidence, we think there's some new kind of particle that's providing the mass. But I agree, it's a testable question, and it's important to find out.
When you say based on the preponderance of evidence, if we haven't discovered dark matter yet, what's the evidence? It's so preponderant.
So, well, we've seen it through its gravitational effects, including the bending of light.
Yeah, but see, then again, you're going back to the theory of gravity, which, and again, why couldn't gravity just be different on the large, massive scale?
Yeah.
You keep applying the same rules of gravity that we see here on Earth.
Well, it's a little more complicated than that, and it's hard to fully explain it here. We'll probably just cut it short and say, based on sophisticated modeling of the way gravity works on different scales, including through the effects on the cosmic microwave background, it appears to us that there is additional matter, and it's not just a modification of the law of gravity. But I agree, it's a worthy question, and I encourage you to keep thinking about it. Let's give someone else a chance.
Please.
I'm not an academic, but I find this stuff fascinating. But I've always been intrigued by something that I have never got an answer to. Unless I'm mistaken, I believe Einstein defined gravity as a warpage of space-time. But that doesn't tell me how it works. I mean, being just an ordinary lay guy, an ex-factory worker, how would you explain the mechanics of gravity itself? I mean, the warpage of space-time doesn't really give me any details about how it works.
What do you do? Rubber sheet? I'll take that one. I'll take that one. So imagine you have a trampoline, like an ordinary trampoline, and you let a bowling ball in the middle of it. Then, it funnels it down, right? A little bit. And then you could take a tennis ball and throw it into the trampoline, and it could kind of orbit around the cone shape made by the bowling ball, right? So one thing you could say is, well, the tennis ball that's orbiting around is attracted to the bowling ball, or you could say the bowling ball warps the space, making that kind of a dip, and the tennis ball just responds to the change in the shape of space. And that's a way of thinking about how the sun communicates the gravitational effect to the planets. And one cool thing about that is, in the Newtonian theory of gravity, there's a good explanation of why the planets orbit the sun, but light passing near the sun would be unaffected. Yeah, I don't know how to make less noise. There we go. There's a feedback loop, but I don't know how. Okay, there we go. All right, he's an experimentalist. So, I'm a theorist. I just identified that there was a problem. So hang on a sec. So in the Newtonian gravity, the sun basically exerts some magical force on the Earth, and the Earth feels it, and the Earth goes around. But light would just go right past. But in Einstein's theory, where the sun warps the space-time, like that analogy I gave of the bowling ball and the trampoline, even light, as it follows over that surface, would be bent. And that effect is observed. So that's one way we try to explain it. It's hard to imagine 3 dimensions warped. I can't do it either.
I mean, from a practical viewpoint, even gravity itself is a mysterious force.
Yeah. Yeah. So I totally agree. Gravity is mysterious. That's why we're working on it.
It does strange things, and the theory predicts very strange things, but every strange thing that it has predicted has been measured. So, for instance, it predicts that clocks will move differently. They'll count time differently. The passage of time is different if you're here on the surface of the Earth, or if you're in an airplane or in space. And in the 1950s, people took these clocks onto airplanes.
I believe that is used in a practical sense.
Your GPS system.
Yeah, GPS.
Yeah, so, GPS would not work if we didn't understand the special and general theory of relativity. It's pretty amazing, right?
Right.
And that's because we want the precision of, knowing where we are to, 10 meters or whatever.
Even though it's a microsecond, it adds up.
Exactly.
My Physics 3 students here remember some problems that they had to solve where they had to figure out how off would GPS be if you didn't account for general relativity.
By the way, the first 2 questioners both opened by saying, I'm not an academic or whatever, but you both had really good questions. So nobody else has to apologize for their questions, starting on from here on out.
Another thing about your question is you say, how does it really work? Well, that warping of space-time and all, that's just that tells us the framework of the equations, right? And that helps us build models and make predictions. But that's the best science can do. That just helps us predict one thing, says if we see this, that means something else. There isn't any, hey, this planet talks to the other planet and says, come over here. We don't have that. All we have is a little math model that says, if my planet's here, where's it going to be tomorrow? And that warping picture helps us picture that. It doesn't mean anything's explaining. We don't really know how it works. All we have is this little idea, this math model that tells us how to make predictions.
I think we know how it works. We don't know why it is the way it
Okay,
is.
sure, we don't know why it is.
And, you know, if we didn't know how it works so well, we wouldn't be able to make GPS work. We wouldn't be able to put a satellite, you know, sent from Earth to get to Pluto at exactly the right time and exactly the right speed and exactly the right place to be able to take photos of the surface of Pluto.
One quick other question. In the presentation, it was mentioned that gravity is one of the weaker forces.
Weakest, yes.
Compared to,
Like electricity, magnetism, and the nuclear forces.
Yeah, you take an atom, proton, or an electron going around a proton. They're pulled together, electric forces attract. They also have mass, so they pull each other together. The electric force is 10 to the 40 times stronger. So that's 140 zeros. So that's way stronger.
Yes. Okay. Until all of the experiments kind of move these out, what do you think? This is probably just going to be a guess on your part, but how likely do you think it might be that more than one of the proposed hypotheses about gravity is possible?
I think it's 100% possible that it's a mixture of things.
I like the axion hypothesis, but it doesn't seem like there's enough light being generated in stars to...
And we come up with these simplest ideas. Think about us. Right? I'm sure we think we're just this tiny 5% of the energy in the universe. We're super complicated. We got protons, electrons, neutrons, but then we say dark matter is one particle. That's just a simplification so that we can, you know, have a first step. But I think it's almost 100% possible that it's a mixture of, or a more complicated thing we haven't even thought of.
Yes, so at the beginning of your talk you touched on a universe of matter as opposed to a universe of antimatter. How would you describe what antimatter is?
Well, it's just like ordinary matter, except it has reverse properties, reverse charge. And it's the kind of thing where the antimatter partner to the electron is something called the positron. And things like its mass are the same, and other intrinsic properties are the same, but its electric charge is opposite to that of electrons. And when matter meets antimatter, it annihilates into energy. Is that answering what you're asking?
So, you know, that's the whole E equals MC squared thing, or part of the story. You know, if you combine an electron with an anti-electron, people say, oh, you get pure energy. Well, what form does that pure energy take? It takes the form of 2 gamma rays, or 2 photons of light. And just, likewise, you can run that in reverse. You can put light in and you can make matter appear. I think you had a question in the back.
Yeah, so in one of the experiments we're talking about how you have atoms sitting there. Are you waiting for them to be hit by dark matter and then you see a light reaction, or what are you waiting? Are they going to be hit by dark matter?
Yeah.
Repeat the question.
I think the question is, what are you doing in order to let some targets be hit by dark matter? And you said something about waiting for light from them. So I think you're referring to, for example, the LZ experiment that I talked about, where they've prepared ordinary atoms, xenon atoms, in a state so that if they were bumped by dark matter, they emit light. And they also ionize nearby atoms, and they take those electrons and with an electric field and drift them up to a place where there's gas, and that creates a second flash of light. And by looking at the different combinations of the strengths and timing of those flashes of light, you can tell whether it was dark matter that hit it or some type of radioactive background. They have seen light flashes. Thus far, no one has seen evidence for dark matter from that, though. They've seen evidence for background, which they've been able to very clearly identify as such. But none of the experiments have incontrovertible evidence for dark matter. But let me step back from that a moment and say there are a number of experiments which have had potential signals, what looked at the time at least like potential signals of dark matter. Thus far, each of those signals has been different from the other. That is, the dark matter candidates that could have made those signals were different from each other. And no one has been able to reproduce the strongest, the most long-lived evidence for dark matter, which came from a crystal-based experiment, which I didn't describe. So they have a signal, and in some ways it behaves like dark matter. But in order to accept evidence that you've seen something extraordinary, whose properties we really don't know, you need to be able to reproduce the results by different people using different techniques. So far, no one has been able to do that.
I could be wrong on this, but at CERN, do they use lead ions to look? Is that the dark matter still? Do they use lead? No.
They're not looking. Oh, sorry.
I mean, there is an experiment at CERN to collide heavy nuclei with other heavy nuclei. It's not for dark matter. It's just because it's cool.
Are they doing experiments to do dark matter at CERN at all? No.
There is one axion experiment there.
Plus, their proton collisions are searches for dark matter as well. That's a multi-purpose.
Adam should talk that one.
You're right. Yeah,
The collider search.
Yeah, this was mentioned. One thing that you can possibly do is, if dark matter talks to us, collide two protons, smash them together, make dark matter. The thing is, what would that look like? Well, you'd have one particle come in, one particle come out, and you would make nothing. That would look a lot like if two particles just missed each other. So usually what they look for is two particles have to sort of bounce off something else. So you make something that you see, one of the particles that we know, and you look for nothing coming the other way, because that's going to look really strange. Two particles come in, something goes flying off in this direction, nothing goes the other way. So they look for that, and they can use that as a way of testing how strongly something would...
So that would look like a violation of conservation of matter?
Absolutely right, yeah. And the reason they do it with protons is they can sort of get more oomph into a one particle. If you do it with lead, you have to spread that oomph over the whole lead nucleus. So the individual things in the lead aren't going nearly as fast or as energetic. So it's more efficient to do it with protons.
So for the liquid xenon distribution, why are they using xenon atoms?
Well, that's okay. So the question is why use xenon atoms to look for dark matter? And one detail that I didn't go into is the selection of targets. In addition to, you saw that long list of theories and the long list of candidate particles that come out of those theories. Well, each of those candidate particles interacts with, would, if it exists, interact with matter in a different way. And so all the targets that are chosen to emphasize the search for one of those types of candidates. So the type of candidate that they're looking for in the LZ experiment is one which interacts with the nucleus as a whole. And there, the effective size grows as the square of the number of protons and neutrons in the nucleus. So you want a big, heavy nucleus. There are other experiments like ours, which are looking for a different candidate, which interacts with something called the spin of the nucleus. And there you want to have individual protons or neutrons in the nucleus that are ideally suited for looking for that type of candidate. So each type of target particle is selected because it's probing one candidate dark matter, or ideally you'll choose targets that search for multiple candidates. But those are the kinds of considerations that go into selecting a target atom. Yes, because of its mass. So they're looking for it with a large number of neutrons and protons in there. We used to do the same. Right now we use one fluid, which is a firefighting fluid, C3F8. The fluorine atom happens to be very good for looking for dark matter that would interact with the spin of a nucleus. But we used to use a different chemical, CF3I, another firefighting chemical. And we used that because the iodine atom has so many protons and neutrons in it, 127. And so the chance of interacting with dark matter that looks at the nucleus as a whole would be greater for iodine than fluorine. So you choose your targets based on the type of candidates you're testing.
I mean, there's also a lot of practical considerations. You can make a large vat of clear liquid with all of these things, as opposed to, say, like a bucket of lead. So, you know, those kinds of things and the rejection of backgrounds go into what you could do, because the whole point about the detector is it has to be huge, and if it makes a little flash of light, you want to be able to see it, so it needs to be clear, and you know, there you go. That kind of thing builds it up. What you in the front there?
Yeah, I have two questions mixed together. What would you say is your favorite thing about being a theoretical physicist, and in your career, what has been your biggest accomplishment?
The question is, what's my favorite thing about being a theoretical physicist?
I'll take that.
Go for it. And what's the biggest accomplishment? My favorite thing is I think this stuff is fascinating, and I get to think about it every day. So that, I think, and I hope to continue to do it as long as I, stay employed. Biggest accomplishment? I don't know. I don't know. If I'm being a theoretical physicist, I get to be wrong lots of time, think about some crazy thing and say, oh, hey, maybe this is what's going on, and explain something. I guess lots of accomplishments. I guess the thing I like most is having an impact on the experiment. So convincing somebody who's working on an experiment, dark matter experiment, collider experiment, saying, hey, this idea is good enough, go out and look for it. And somebody does. And most of the time it gets crossed off as not right, and it's cool that I can be not right all the time. But it means, I think science is advancing that way. We're learning something. It might be slow, not this, not this, not this, but stuff is going forward. So that's my take. But
Good question.
you're not going to answer that one? You're a theoretical physicist, too.
If you guys have different experiences, I'd like to.
No, I pretty much agree with it. It's a good question. There was a guy in the back there.
I was wondering if when you look at the different galaxies, if the dark matter content is the same in all of them, or if there's some galaxies that have higher or lower contents of dark matter?
Yeah. So that's a great question. The question was, do all galaxies have the same amount of dark matter? If they do have dark matter. So it appears, no. It appears that there are some galaxies that, let's say we think we have this much dark matter. So like say this is a certain amount, and here's the same certain amount. Some of these galaxies have a pretty large number of stars, like the Milky Way. But then there's some other galaxies that have, we think, a similar amount of dark matter, but many fewer stars. And one of the interesting things to try to understand about the way the universe works is, why is that different? There should be, well, it's interesting to ask, why is it different? Why is it almost the same? So that's part of what we're trying to figure out of, we don't want just the, so if you ever buy a can of like soup or whatever, it lists the ingredients on the back. And that's sort of where we are with the universe. We know it's, 74% this and 24% blah, blah, all that stuff. It doesn't give you the recipe. So the thing we're trying to figure out, first we have to get the ingredients list, and then we want to try to reverse engineer the recipe of how things get put together and why they look the way they do. Because with those same ingredients, I guarantee I could make something that tastes a lot worse.
Yeah, I was wondering, based on the standard model explaining matter, it sounds like for dark matter that the standard model won't work. That you need different type of things. I'd like you to comment about that. And the other question is about dark energy. When we're talking about dark matter, and I'm reading up for this, I kept coming on this dark energy.
So the question is, we got a standard model. how does dark matter fit into that? I guess is question number one. And the second one is, how does this dark energy fit into it? Those are good questions. So first of all, the way I think about standard models is kind of like our periodic table. Periodic table was set up in 1800, you know, you got your helium, hydrogen, et cetera, et cetera. Those were the building blocks at the time. Everything was made out of that stuff. Well, we've smashed stuff together a lot harder, and now our periodic table is the standard model. But when people had, you know, 100 elements in that periodic table, they didn't stop. They kept looking for new stuff. And the reason that they thought was the new stuff was there was stuff that they couldn't explain with only their 100 elements. That's exactly the stage we're at right now. We got a bunch of stuff we can explain with our standard model. Dark matter is not in that, so we got to extend it. And that's one of the things that's really exciting. If we were done, nothing left to do. We've figured it all out. But we're not at that stage, not even close. We know that there's stuff we don't understand. So what we try and do is we try and do 1,000 different experiments saying, well, maybe it's kind of like this, maybe it's kind of like this. And that's going to allow us, hopefully one day, to figure out what is that extra element to put in our new periodic table. And then we'll go from there, look for the next new thing. Now, dark energy is very different. All the stuff, matter, that we've talked about so far, that all clumps together. You put it, and it's going to start clumped together. If I make a bigger box and I have the same amount of matter, that matter's more dilute, it's more spread out, right? If I have 3 water bottles on this table, if I put in 9 tables and I keep only 3 water bottles, I have fewer water bottles per table. Dark energy doesn't work that way. It's like me expanding a new table and putting a new water bottle. Every time I expand space, I get more dark energy, more and more and more. So it's totally different. It's not matter at all. It doesn't clump together. It's just sort of a constant amount. I keep expanding, I keep getting more of this stuff. So it's not a particle at all, which means it's really weird. It totally blows my mind that we think 74% of the universe is completely alien compared to the stuff that we know as matter. So we know nothing about it. So dark matter, we say, okay, that's probably a little particle, something that would clump together, something that would get less dense if I put the same amount in a bigger amount of space. Dark energy is not like that at all. So we know it's zero about it. All we know is it is not like matter.
But is they talk about the dark energy fueling the expansion of the universe? So how does that fit in? What would be driving it?
Well, it still has energy associated with it.
Not the energy wasn't normal.
Exactly. A totally different type of energy. So we can write down, usually we think about energy as being energy that it costs to make this thing, energy that would we put it in if I throw it. Dark matter, dark energy is a third different kind of energy. It makes it, you know, fascinating and totally frustrating because we only know how to study, you know, matter kind of stuff.
When you talk about dark energy, the whole concept of a photon is alien.
Absolutely. Yep, it's a different type of energy completely.
So it's going to be some light particle like a photon?
It's not a particle. Yeah, it's not a particle. No. If it was a particle, we might. It's part of the thing that's difficult about it, because if it was a particle, we know how to study particles. You smash other particles into it, you study how it bounces off, how to react. Dark energy, it's not a particle. You can't do that.
So you can't detect it at all at this point?
We can't detect it on a small scale. You can see how it impacts things on a big scale. But
To explain the expansion of the universe?
Pardon me?
You say you're using it to explain the expansion of the universe?
It's used to explain the acceleration of the expansion. Just to explain the expansion, doesn't need dark energy. But to explain the fact that it's speeding up, does. So, actually, I have a question for you, sort of. I want to say it's fun. I'm visiting town for the day, and it's fun for me to come to an event like this and see something like more than 100 people who are interested about learning more about physics, and I think that's really great. And I want to ask you all to just wave hi. So I've never taken a picture from the stage before, so I just thought I'd see what it was like. And, another thing I want to highlight is, I think you're fortunate, and our, field of physics is fortunate to have people like Dr. Levine who are both, experts in the physics. He probably soft pedaled it, but he's, a world-renowned expert at making these dark matter detectors work. But the other cool thing about him is that he's really committed to bringing that science to the public. And I think, like I said, the field of physics is lucky to have him, and I think South Bend's lucky to have him too. So let's thank him. This guy, he works for the other school, so let's not talk about him. Oh, he's a good guy too.
Any questions?
Yeah. He's back.
We still didn't figure it out.
Yeah, it's only been like 20 minutes.
20 minutes!
Yeah.
That you're looking for dark matter as such a tiny, tiny, tiny thing. Is it safe to presume that all the theories say that dark matter is subatomic, neutrino size?
No, actually. No, primordial black holes?
Yeah, no, I talked about black holes. Those were from the ad hoc class of ideas, those black holes made in the very early universe.
Yeah.
And those could be the size of asteroids. Now, we do have limits on, we know the black holes can't be very, very big because we would have seen them, I didn't talk about this, we would have seen them in searches in the Milky Way for evidence of them passing in front of other stars. And from the gravitational lensing that Dr. Beacom talked about, on the large scale, we would have seen it in the small scale in the Milky Way. So we know they can't be too big. We also know they can't be too small because one of the things that we know, thanks to Dr. Hawking, is that very small black holes evaporate and explode into light. So we have limits on the candidates of dark matter that could be that could be much larger than a single particle. And if you looked on my graph, black holes were really up there. Those were pretty large, but that's why that scale of possible value for dark matter particles was so very large.
So what's that, a range again?
Trillion.
Yeah. So it's possible that dark matter has a fairly large mass because of, say, black holes or whatever.
If it does, there's none here.
Well, that's right. So there's none here right now, and we'll never, in that case, we wouldn't find it in an underground detector or at a collider or whatever. We would have to find it some other way.
So in addressing that particular theory, if dark matter is these little black holes, it would be much, much bigger than something the size of a neutrino.
Yeah.
There would be none of them in our galaxy.
Well, they would be in our galaxy.
But there wouldn't be one in this room.
Wouldn't be one in this room?
The bigger the mass of any individual dark matter candidate, the fewer of them there are. So they would still be a large number, say, in the Milky Way galaxy, because we know that dark matter is spread smoothly throughout. It's not clumped like at the center. So astronomers are actually looking for candidates like this too. If a dark matter asteroid, say, goes through a star, they look for flickering in starlight. That would be a signal of a black hole hitting a star. So that is something that's being looked for. But I don't know if I intentionally or not, sort of demoted that as a somewhat ad hoc idea because it was invented just to explain dark matter, and there's no particular reason people have come up with why the universe or a mechanism that people would have come up with to produce such a thing.
Yeah, when did you start thinking the theorists were right?
Well, I just spent the last 15 years looking for dark matter that has been predicted by other theorists. So I'm not blaming you guys, that we haven't found.
We have to keep an open mind and search in different ways.
It could be any one of the things on that long list, a combination of them, as you were suggesting, or it could be something no one's thought of yet.
So if it were anything bigger than this neutrino-sized piece of dark matter for which you search, we'd see them much more easily? Why
Not
wouldn't they
necessarily.
be here? If they're all over the universe,
Yeah.
why wouldn't they be in this room, or at least on this planet, or at least in our solar system? We could see them out there banging around.
They
well,
could
okay,
be.
let's put it together this way. Suppose there's, let's see, suppose there's 1 million euros of currency in South Bend. So European currency, 1 million of them. And we don't know if there's 1 million €1 notes hanging around and everybody's got several of them, or nobody's got any of them except one person has a single note that's worth €1 million. But we do know the total amount. So in a similar way, we know the total amount of dark matter mass in the galaxy. And as Ilan said, if we say the mass per particle is small, there's a gazillion of them. If we say the mass per particle is large, there's fewer of them. And then so maybe there's not, if there are few, maybe there's not one in this room on average, but there has to be a certain amount to make up the known mass.
So the only way we can look for them is by presuming they're tiny, then we know they're here. We can see
Yeah,
them.
so the tiny ones can be detected in the underground detectors and things like that. If you make them more and more massive, then they would be too rare. You're quite right, and it would never pass through his detector. But then there's other ways to find those.
And astronomers are looking for that.
Right.
But there you have to look at the 400 billion stars in the Milky Way galaxy and looking for the flickering that I was talking about from these effects.
So if there's one particle of dark matter in my hand, like that was the analogy, so how can we not detect it in a detector if we know there is one in my hand?
Yeah, go ahead.
So when you detect something, when you detect sunlight, you're feeling a photon that stops on your face and transfers its energy to your skin. If you have a particle, so the question is, if you've got a particle on average in your hand, how come we don't see it? How come we don't feel it? How come we don't catch it? Well, in order to catch it, you have to be able to stop it and transfer its energy to you. But one of the properties of dark matter is that it interacts so very weakly, i.e. rarely, that it just goes through your hand. So it's not like you're holding on to the dark matter particle, it's just passing through the space that your fist resides in at that moment, but you're not catching the dark matter particle. Now it sounds like an impossible idea, but if you hold out your thumb, every second 100 billion neutrinos from the sun go through your thumb. You don't feel them because they also interact only weakly with your body. And so you don't sense them, and you need very, very special sensitive detectors like the snow experiment, which we saw. That's what I worked on before, looking for dark matter. And there we had 1 million liters of heavy water to detect about 20 neutrinos per day when you get 100 billion per second through this small area. So that gives you perhaps a sense of how rare the interactions are and how you can have it in your hand and not feel it.
So, one way to think about it is, as Ilan was saying, if you see photons that are coming right from you can't see into my hand, right? You don't know if I'm an alien-human hybrid or whatever, or for flesh and bone, right? But with X-rays, you can see through, and the X-rays mostly get through, but some of them scatter. And now imagine something that scatters even less, and then you're on your way to thinking about dark matter. You did.
Don't need you guys anymore.
So you talked about basically there's dark matter in all the galaxies and whatnot. So we know that there's some here, and you used your analogy with the Euro and South Bend. Well, do we know how dark matter interacts with itself at all, and if it has any kind of structure to it that could help us maybe narrow down our search area?
The easy answer is no, we don't know.
The only thing we know for sure is that it is massive, so it experiences gravity. Like I said, it clumps together, pulls other stuff that have mass. But it could have other interactions too. Lots of people think about this, think about the implications it would have.
Like, so what if the dark matter sector has many different particles in it, like you talked about
Yeah,
earlier?
that totally
So
allowed.
those could be interacting strongly with each other.
Sure.
So there could be like a whole world of dark matter particles, sort of analogous to our own, where they interact strongly with each other and make dark atoms and dark planets and all of that stuff. But we don't think so, but it's a possibility.
So is that where our idea of dimensions comes from?
No. Yeah, that's just different.
Kind of different.
And so could that be related to the Oort cluster? How it seems like the clumps of dark matter travel it's like they're interacting with each other and they stay with each other as the two galaxies pass through each other.
Absolutely. The bullet cluster is one of the things that people use to set limits on exactly how strongly dark matter could talk to itself. Absolutely.
Because the two dark matter clumps went right through each other.
Go right through each other.
But you're asking a separate thing is why is it a clump? And that's due to gravity, not due to scattering.
The dark matter is also traveling with all the galaxies that were in those clusters. They also pass right through, and they're coincident with the dark matter. It's just the unaligned or unbound individual atoms that have been left behind, but all those galaxies passed right through with the dark matter. And it's gravity, but scientists are definitely looking at these different possible rich interactions between dark matter. And you have all sorts of names that are analogous to names for particles that exist in ordinary matter, like dark photons.
One more question. Why don't we maybe wrap up and
Please.
go to your demos
Yeah.
in the back? Go ahead in the back.
If dark matter can interact even weakly with our particles, where it would bump a particle and impart some energy, and then we could see that, would the dark matter then lose energy, and then eventually all dark matter would fall into the center of the gravity over time?
That's an awesome point, and it's correct. And the reason that doesn't happen is that the dark matter scattering is so rare. That's one of the ways that we know that the dark matter scattering probability has to be very low.
What I think we should do now, first of all, let's thank our two guests who've taken time out of a very busy schedule to join us and answer our questions today. Dr. Adam Martin from the University of Notre Dame and Dr. John Beacom from The Ohio State University. And thank you all for coming out here. Now, I'll be happy to stick around and answer questions one-on-one, but I also want to point out that in the back, my students have set up some interactive displays where you can see certain things that we do in the lab to help us in our search for dark matter, including some of the broader impacts. We're helping a local luthier understand how to model jazz archtop guitars. In fact, Tom, if you wouldn't mind standing up, Tom Nania founded the House of Luthiery after graduating from IU South Bend in, was it 2012? 2012, and has founded a luthiery here and has been engaging in scientific study of instruments to be able to do something similar to what people have been doing since the 1960s with violins that have been able to reproduce violins that are acoustically identical to the Stradivarius line of violins. He's trying to do the same thing with guitars, and we're working together trying to help him with that. And so he's got some displays back there, as well as, I guess, Nathan Walkowski is back there. He'll demonstrate some of the other acoustic stuff that we're doing in support of the dark matter experiment. And I'll also be happy to stay and answer questions. But I think Dr. Martin and Dr. Beacom have already had a very long day, and I very much appreciate your sharing your expertise with us.
Happy to be here, and I want to thank everybody for their great questions and especially for their interest in science. Thanks.